Good day and welcome back to the second installment of Calculus of Vector Valued Functions. Now in the previous video we introduced the concept of differentiating a vector valued function and really focused in on finding tangent lines. And that's exactly where we are going to pick up and start for this example. Now as mentioned, a common question is going to be of the form given here. Find an equation of the tangent line to some curve at some point. And this is exactly what we finished with on the previous example. So this will be a great opportunity for you all to practice. So first, let's kind of draw a picture together to get a geometric idea of what this looks like. And then I'll give you a few minutes to compute out that tangent line. So on this helix, because it's of the form, cosine, sine, and t, this t is indicating that it's wrapping around somehow the z-axis. Because it's two cosine and a single sine, that's just kind of telling us that it goes, a bit further out in that cosine direction than it does in the sine direction. So let's go ahead and just sketch an arbitrary representation of this curve. Remember, it doesn't have to be, precise or identical to what it's supposed to be, but just give us a general idea. So we are rotating around the z-axis. And at the point 0, 1, pi over 2, which looks like it could be about right there. So I'm thinking that we go out 0 in the x direction, 1 in the y, and up pi over 2 in the z direction. If we sketch the tangent line at that point, roughly speaking, it might look something kind of like this. What we would like to do is find the equation of this tangent line. So I'm going to go ahead and ask you to pause the video, take hopefully just 2 or 3 minutes, use the previous example as a template or a blueprint, see if you can come up with the equation of that tangent line. Okay, so assuming that you paused the video, let me remind you that the generic form of the equation of the tangent line is going to be something of the form xyz is equal to r of, and I'll write t sub p, the parameter value corresponding to our point, plus t times r prime of t sub p. And if we are at this point 0, 1, pi over 2, if we specifically focus in on the z component, that's telling us exactly what t is equal to. This is telling us that t is pi over 2. So our tangent line has the form r of pi over 2, which is 0, 1, pi over 2, so the vector corresponding to the point, plus t times r prime of pi over 2. And I'm going to leave a little bit of space, and just below, let's figure out the value of this derivative. And we differentiate a vector valued function term by term. The derivative of a cosine is minus sine. The derivative of sine is cosine. And the derivative of t is 1. So r prime of pi over 2 is equal to minus 2 sine of pi over 2, cosine pi over 2, and 1. And something I will ask you to do, and I will hopefully remind you of this frequently, is we should always evaluate functions at common values. So for example, a trig function at one of those common angles. Think 0, pi over 6, pi over 4, pi over 3, multiples around the unit circle. So we should be able to substitute in the values for sine of pi over 2 and cosine of pi over 2. So sine of pi over 2 is equal to 1. Cosine of pi over 2 is equal to 0. So the equation of our tangent line in vector form is as follows. And all we need to do is cut and paste, and lastly, substitute in this vector that we have just found. Now that we've worked through several examples of finding equations of tangent lines, Let me note that many of our differentiation rules from the past can be extended to this sitting of calculus 3 and vector valued functions with just a few minor modifications at certain points. Now, the first two differentiation formulas are very familiar and they extend directly. If you want to differentiate a sum of vector valued functions, we can do that no problem. We take the derivative of the first plus the derivative of the second. And it works out exactly the same if it's a minus sign separating the two instead of a plus. Similarly, if you have the derivative of a constant times a vector valued function, just like we've always done, you can pull that constant in front of the derivative. And then what comes up next are several variations on the chain rule. So if we would like to differentiate a scalar function times a vector valued function, the product rule would suggest that what we should do is take the derivative of the first times the second plus the first times the derivative of the second. And that is our first version of the product rule. We can do the exact same thing over the dot product. We can think the derivative of the first times the second plus the first times the derivative of the second. And the only thing changing here is what it is we mean by times. So if we start off with the dot product, it's the derivative of the first dotted with the second plus the first dotted with the derivative of the second. Similarly, with the cross product, we would have the derivative of the first crossed with the second plus the first crossed with the derivative of the second. So we have, I guess, three variations on the product rule, but they're all essentially telling us, the exact same thing. And lastly, let me note here, there is a variation of the chain rule where we have this composition, u of f of t. And whenever you have that language with the word of in there, u of f of t, that's an indication that we have a composition and we need to use the chain rule. And the chain rule tells us we take the derivative of the outside, we evaluate it at the inside, and then we multiply by the derivative of the inside. And note that the derivative of the inside is really kind of a scalar function. So we multiply it through the vector just like a scalar quantity. And this is a chain rule. To continue on our discussion of the derivative, I'm now going to flip to page 4 to see kind of a more theoretical type question. So on page 4, we're asked maybe a seemingly weird sounding question. What must be true about the vector valued function r of t in order for r and its derivative to always be perpendicular? And I want to note that a key word is always. A common misconception is to believe that r and its derivative r prime will always be perpendicular to each other, opposed to just saying that r prime is tangent to r at a point. And just to really hammer in the idea that this is not something we should expect to always be true, I'm going to write down a quick example. So no, r and r prime are not always perpendicular. For example, if r of t is something as simple as t, r prime of t would be 1, 1, 1, and r dotted with r prime is 3t. Multiply those corresponding components and add them up. And in order for this pair of vectors to be orthogonal or perpendicular to each other, their dot product would have to be 0. But their dot product is only 0 when t is 0. So let's just go ahead and note, and only perpendicular or orthogonal at t equals 0. So certainly not perpendicular always. So what would it take in order to make that be true? So let's go ahead and start off with what we would have to have happen. So if r of t dotted with r prime of t is equal to 0, what can we do with this? And the reason I'm making this assumption is, i.e., r and r prime are perpendicular. And this is not a kind of obvious way to go about things, but it's really kind of a nice way to see some of these properties we've previously discussed, as well as foreshadowing what we're going to see in this next upcoming section. So I'm going to note that if something is equal to 0, we can always add it to itself. That is to say, 0 plus 0 is equal to 0. And I'll just note that to the side here. We've just really said 0 plus 0 is 0. So nothing too crazy, I hope. Furthermore, the order that we take a dot product, we said, does not matter. So with this second part, we can write this as r prime of t dotted with r. And the reason we can do this, just to kind of give an explanation, a dotted with b is always equal to b dotted with a. The dot product is commutative. And now if we compare this with our formulas on that previous page, this looks an awful lot like a product rule. The first times the derivative of the second plus the derivative of the first times the second, where the first and the second function happen to be the same thing, r dotted with r. So using the product rule. And finally observe that if we go back to our beginning of our discussion on the dot product, we said that a vector dotted with itself is simply the magnitude of that vector squared. So this would be a property of the dot product, or we might say property of just vectors in general. So what we've seen at this point is that if we have r dotted with r prime is 0, then the derivative of the magnitude of r of t squared is equal to 0. And what's the only way the derivative of a quantity can be 0? If that quantity itself is a constant. So this is telling us that r of t must be equal to a constant. And if r of t is equal to r of t squared and modulus is equal to a constant, the modulus of r of t itself is also a constant, just the square root of it. And if r of t and r prime of t are, and remember the key word here, always perpendicular, then r of t is equal to, I'm just going to simply say k, where this k is a constant, which is exactly what we've seen from this above work. And as mentioned, this is not an easy thing to do, but hopefully kind of in retrospect, you can go through step by step and see kind of how we've justified this work. And just for fun, a different way of saying this would be that r of t lies on a sphere centered at the origin with radius k. And that completes the material for this video. In the next video, we will turn our attention to the integral of a vector valued function. So stay tuned.